This is a short version of the notes from sections 1.5 and 1.6. 1.5 was on inequalities. We're talking about compound inequalities. Main thing here, for an and statement to be true, both of these statements must be true. If we are graphing an and statement, we are going to shade the overlap. For an or statement to be true, either statement could be true. For an or statement, we are going to shade each inequality because either of them could be true. So for an and statement, we want to shade in the overlap of the two inequalities. For an or statement, we're going to shade in each inequality. So for example 1 here, we are asked to graph on the number line x is less than 8 and x is also greater than or equal to 2. So to do that, because it's an and statement, we are looking for where these two graphs overlap one another. So up above here, I'm going to graph each one individually. X is less than 8 looks like that. X is greater than or equal to 2 looks like that. So we want to know where both of those things are true. They're both true at 2 because they're both shaded in at 2. They're both true in between the values, but not at 8. My final graph should look like that. This one's similar, but an or statement. For an or statement, we shade in everything for each graph. So when I go to graph this or statement, I need to shade in everything for x is less than 8, because if x is less than 8, the whole statement is true. So I shade in everything less than 8. X also could be greater than or equal to 2, so I need to shade in everything greater than or equal to 2. And that is going to include that 8 that I did not shade in the first time. And notice in this case, my entire number line gets shaded. So that is graphing inequalities, or graphing compound inequalities. Let's talk about solving this one. We are trying to get x by itself in the middle. Anything I do to the middle, I need to do to the outsides as well. So here I need to subtract 5, get rid of that adding 5. And you're going to subtract it from the left and the right side if you subtract it from the middle. So I've got 13 is less than negative 2x is less than or equal to 22. Divide both sides by negative 2. Divide all sides by negative 2. When I divide by a negative, we need to make sure we remember to flip our inequality around. So the best way to write this, we start with the smallest number, negative 11. X is bigger than or equal to that. X is less than negative 13 over 2. If it's written as one line like this, that is an and statement. We need x to be greater than or equal to negative 11 and also to be less than negative 13 over 2. 1.6 is on absolute value equations. If you think about this basic absolute value equation, the absolute value of x is equal to 3. X could be 3, but then x could also be negative 3, because if I take the absolute value of negative 3, I also get positive 3. So notice we could get two solutions for these. So for this example here, we need to start by subtracting 7. Get rid of that 3 by dividing both sides by 3. And And then once we have those absolute values by themselves, we can say 2x minus 9 could be equal to 5, or 2x minus 9 could be equal to negative 5, because if it is, I would take the absolute value of negative 5, and I get positive 5 there also. And then we solve for x. Add 9 to both sides. Before you circle your answer and move on, you have to check your solutions. It's possible to get what's called an extraneous solution, which is an extra one. It spit out an extra solution. It's possible that they're both extraneous and the answer is actually no solution. So to check them, plug them back into the original equation. 7 times 2 is 14, minus 9 is 5. Absolute values is 5 times 3 is 15, plus 7 does give me 22. And you will find when you check 2 times 2 is 4, minus 9 is negative 5. Absolute values is positive 5 times 3 plus 7 does also give me 22. They do both check this time, but it's possible that one or even both of them does not check, even though you didn't do anything wrong. Looking at this one, we're going to do it the same way. Get the absolute values by themselves. In this case, they already are. And then we're going to set up two equations. 3x minus 4 could be equal to this, or 3x minus 4 could be equal to the opposite of this, which is going to be positive 4x plus 1. Once we have our two equations set up, we solve for x. And then it's very important to check your solutions. One like this, you would be allowed to use your calculator to check it. I want to show you the fastest way to check it on the calculator. So if I'm checking 3/7, we want to store 3/7 as x, so that every time I type an x on my calculator, it's going to plug 3/7 in there. To do that, we do 3 divided by 7. There's our 3/7. Store, which is right here, it's above the on button, STO with an arrow, and then x. X is right here next to alpha, and push enter. And now when I type in x, it's going to replace that with 3/7. So I want to type in each side of my equation. I'm going to type in this side. To get an absolute value is under math, scroll over to number, and then it's the first one here, ABS. And I want 3x minus 4. 3x minus 4. So when I plug in 3/7 to this side, it gives me 2.714. I want to plug in 3/7 to this side also and see if I get the same thing. Negative 4x minus 1. Notice they are not the same thing. They're almost the same thing, but this one's negative, that one's positive. So 3/7 did not check for me. I should still see your work for it, but it's an extra solution, an extraneous solution. Now we're going to check negative 5. So we want to store negative 5 as x. So we type in negative 5, store, right above on, x, right next to alpha. Enter. And then instead of typing these in again, you can just scroll up. And once that is highlighted, you can push enter to say that's where I want to plug it in. Push enter one more time. So when I plug in negative 5 into this side, I get 19. Plugging negative 5 into the other side also gives me 19. Therefore, x equals 5 is a solution.